Step-Wedge and cluster trial design as part of our research methodology lecture series. And just as a brief introductory bio, Monica Taljaard is a biostatistician and senior scientist in the clinical epidemiology program at the Ottawa Hospital Research Institute and a full professor in the School of Epidemiology and Public Health at the University of Ottawa. Her main research interests are in the design, analysis, and ethics of pragmatic and cluster randomized trials. As a methodologist with the Ottawa Method Center, she collaborates with clinicians and researchers from a variety of backgrounds in the design and analysis of clinical trials and observational studies. And with that, Monica, I will turn this over to you.
Great, thanks very much. So I will share my screen, hopefully the correct one. And so you should now be seeing my screen. Let me know if not. So thank you very much for the introduction, and it's a real pleasure to be here and talk on cluster randomized and step-wedge trials, which I find really interesting. So what I wanted to accomplish today, and so this is pitched at a very applied level, and it happens to be more or less the same talk as I gave last year. So apologies if you already listened to the whole presentation last year. Hopefully that's okay. But what I wanted to cover was just kind of explain what are these types of trial designs, cluster randomized and step-wedge trials. I want to explain the concept of intra-cluster correlation, which is a critical issue that statisticians and also clinicians have to be concerned about when they are thinking about designing a cluster randomized trial. Then I want to address some potential risks of bias and how we might be able to design our trial to avoid these risks of bias. And I want to talk about some advantages and disadvantages of adopting this stepped wedge, this novel type of stepped wedge cluster randomized trial design. And then I'll conclude with some additional tools and resources where you can get more information. If we don't have time, I'm happy to make the slides available if that would be useful. So I'll start by just contrasting patient randomized trials and cluster randomized trials. So these are the two main types of trial designs. In the case of a patient randomized trial, so that is the usual way in which we design a multi-center, say, multi-center patient randomized trial. Here, we might have, say, 4 centers participating in the trial, and then within each of the centers, we recruit patients one by one. And as they get recruited and they sign the informed consent document, they get randomized to either treatment A or B, or it could be treatment or control, right? So, but the key thing is that this happens kind of gradually over time, one by one, and the randomization happens within each of these centers. And by the end of the trial, we have about half typically of the patients within each center would be in arm A, and the other half in arm B. So within each center, there's 2 types of treatments that have to be administered, the intervention or the experimental intervention or the control. And that's very different than in a cluster randomized trial, where it's the entire center that gets randomized and everybody, all the patients within those centers get the same treatment. So the randomization doesn't happen within the centers. No randomization needs to take place. It's the whole center that gets randomized up front. And then all of the patients just get either A or B. So it seems logistically a little bit simpler. And it's almost like, oh, that's a major advantage of a cluster randomized trial. Why wouldn't we do all our trials like this? It seems a lot simpler. So actually, a cluster randomized trial is not a design that I would say is something that we want to do because it's interesting or because it makes our lives easier. A cluster randomized trial is really something that we do because we have no other choice. And that's because there are some key methodological implications for a cluster randomized trial. First of all, we need a larger sample size if we use cluster randomization than if we had used individual randomization. I'll explain all of that now. We have some additional risks of bias that we have to be worried about in a cluster randomized trial that don't happen in a patient randomized trial. So why does that happen? I'm going to explain that as well. And then also they increase the complexity of the statistical analysis. So let me address those in a little bit more detail. So why do cluster randomized trials require larger sample sizes? Well, that's because in a cluster randomized trial, the outcomes that we measure on different people from the same cluster are usually positively correlated. So the responses are similar. That could be because of a variety of reasons. For example, the type of hospital, could be the expertise of the providers associated with that cluster, just population demographics, all sorts of things. Doesn't matter why, but there is some degree of correlation among the responses from multiple people in the same cluster. That degree of correlation is a very important statistical parameter. We call it the intracluster correlation coefficient, or ICC. It just measures the strength of the correlation among these repeated measures within the same cluster. And as a result of this correlation, what we end up having is actually less information about the treatment than if we had randomized individual patients one by one. So we need to increase our sample size to make up for this reduction in the effective sample size. So I just want to explain why this happens in a cluster randomized trial. So if I go back to this little diagram, here, if we add more and more people to the same cluster, we're just adding more information to one arm of the trial, right? We're not actually adding information about the treatment versus control comparison that we're interested in. So adding more people, recruiting more and more people from the same cluster actually doesn't contribute the same amount of information. Eventually, we reach a saturation point whereby recruiting more people are actually not going to give us any additional information. It's because of this presence of the intracluster correlation. We're just getting more similar information to what we already have in our trial. So that's different than in a patient randomized trial where we recruit additional people within each of these centers and they get randomized to different arms, which boosts our power. It adds more information about this treatment difference, which is what we're interested in estimating, of course. So that's kind of explaining why an intracluster correlation is devastating in a cluster trial, but not in a patient randomized trial. So we need to increase our sample size when we do a cluster randomized trial. So that's the first key point. And we know that ethically, there's this imperative to minimize the number of people who are exposed to the risks of research. And so it's kind of a general principle that we try not to recruit unnecessary people into a trial. That's why we wouldn't do a cluster randomized trial if we can feasibly do a patient randomized trial. So, and there are, of course, good reasons to do a cluster randomized trial. You know, sometimes you don't have a choice. You are trying to evaluate an intervention that can only be given to the whole cluster, right? It could be something like a new model of care or some change that's made to the hospital system. Or it could be that you are training providers. And obviously, when you train providers to do a specific type of treatment, you can't untrain them for some of their patients, right? So yes, there are situations where we have no choice. We have to do a cluster randomized trial. But my key point is we need to justify that choice. So the second thing is that a cluster randomized trial is vulnerable to some risks of bias that we don't encounter in a patient randomized trial. And that's because of the way we identify and recruit patients into these trials. In a patient randomized trial, it's straightforward. We recruit the patients before they are randomized, obviously. So we recruit them, they sign a consent form, they say, yes, I want to be in this trial. They don't know what arm they're going to be in, but they've agreed to be in the trial. So then they get randomized. And usually because of the randomization, things tend to balance out between the arms, right? That's the huge strength of a randomized controlled trial, is that In the long run, things tend to balance out between the arms. We get similar patients between the arms. But in a cluster randomized trial, it doesn't work like that typically. In a cluster randomized trial, we often have to randomize the clusters prospectively and then only identify patients. So we often have to kind of wait for the patients to show up for care at these clusters that have been randomized. Patients don't exist yet. And so what happens is the randomization occurs before patients are recruited. And it's sometimes because of the nature of the interventions that we evaluate in these trials, it's quite difficult to blind people, both the recruiters and the patients. It's difficult to blind them to the allocation. So they know they're being recruited in an intervention arm or in a control arm. And so the decision to participate may kind of be influenced by what arm they've been allocated to. And so we often see that, oh, in this trial, we had many more patients recruited in the intervention arm than in the control arm. Or when we prepare our baseline table, we get, oh, sorry, I'll respond to some of the comments later on. So we get the situation that the characteristics when we prepare our table 1, we get characteristics are very imbalanced between the arms. And so that's called identification and recruitment bias. Huge headache for me. If I work on these trials, I always have to kind of say, okay, what strategies can we put in place to make sure that we don't fall prey to this risk of identification and recruitment bias? Okay, so there are things that we can do. Of course, we can try and mask the people who are recruiting patients and the patients themselves to the arm that they've been allocated to. That can be difficult sometimes, but we do try to put strategies in place to avoid these risks of bias. The third issue that I said was that a cluster randomized trial increases the statistical complexities. Yes, that is true. The standard statistical methods that we all know, like simple t-test or a chi-square test, they just don't work. They don't give us the right answer. They give us p-values that are too small. So we cannot just run a standard linear regression analysis or a standard logistic regression analysis. We'll get incorrect p-values because what happens is our statistical package assumes that all the observations are independent, and it assumes each row of data provides, the same amount of information as the previous row of data. And so our sample size is spuriously inflated, and our p-values tend to be too small. So to get correct p-values, we have to use specialized statistical methods. These would be like hierarchical regression or some GEE or some method that treats the cluster as, the randomization unit. So it could be a random effect in a mixed effects regression or a hierarchical regression analysis. So this would account for that intracluster correlation. But there's also a second issue. So most people by now are familiar with the fact that you have to account for the intracluster correlation. But there's a second piece that perhaps is not as well appreciated yet, even among statisticians who maybe kind of have done, one lecture on cluster randomization. Most biostatisticians don't get actual training in how to deal with the complexities of a cluster randomized trial. So the second issue is often not appreciated. And that's related to the fact that we are actually only randomizing a small number of units. So unlike a patient randomized trial where we might randomize, hundreds or thousands of patients, in a cluster randomized trial, the number of units that we randomize, the number of centers, the number of clusters is often very small. In fact, I think we've done a systematic review of a fairly large number of cluster randomized trial. The median in the literature is somewhere around 15 or 18 or something like that. That's the total number of randomization units. And we know randomization works well in the long run. It doesn't really work that well yet when you randomize only a small number of things. So And also our statistical methods, like a t-test and a chi-square test, even a hierarchical regression, all of these methods assume we've got large sample sizes, large number of randomization units. And so to correct for the bias, when we apply these methods to a small sample size, we need to apply what we call a small sample correction. Small sample correction. So these are specialized methods that are available in some statistical packages, not all. So it's kind of just a lot more complex. So these statistical small sample corrections kind of try to address this bias because of the use of only a small sample size here. So if we do not apply these methods, we will end up with p-values that are too small. So I think it would help if both clinicians and statisticians can kind of remind each other, okay, everything is different. When we do a cluster randomized trial, we can't just do the usual thing. We have to kind of think about all of these additional challenges on top of what we have to deal with in any clinical trial. So just highlight, we've got the paper in the reference below, where we kind of summarize kind of the golden rules for doing a cluster randomized trial well. And these are just some of the key recommendations. The first is to use cluster randomization when necessary. We have a good reason for doing a cluster randomized trial. We want to make sure that we implement some strategies to prevent these risks of bias, right? So that often has to do with trying to keep people blinded to the allocation arm, not only the patients, but also the people recruiting them so that they don't skew the recruitment. We want to make sure that we use statistical methods that adjust for the ICC and then use that small sample correction. So the cutoff for what we consider a small number of clusters would be around 40. Above 40, you kind of tend to be okay, 40 to 50. But the vast majority of cluster randomized trials just have a way smaller than 40 number of clusters. Okay, so we do have to be concerned about these small sample corrections. So those are the key highlights for a cluster randomized trial. So in the next section, I will explain what is a Step-Wedge cluster randomized trial. The easiest way to explain this is probably to just give you a diagram. So here is an example of the standard type of design, a parallel arm design, in which we randomize half of the clusters to the intervention and the other half to the control, and they stay in that same arm until the end of the trial. Okay, so this is a very simple standard design. In a Step-Wedge, it looks a little bit different. Okay, so I'll review in more detail what we do in a Step-Wedge. In a Step-Wedge trial, all of the clusters will start in the control and they will end in the intervention. So that, in fact, is one of the most attractive features, I think, that clinicians perceive to the Step-Wedge. It's that all the clusters are going to get this intervention at the end of the trial. So they like that. Note that there is randomization. This is a randomized trial. So the randomization is with respect to the time when the clusters cross over from the control to the intervention. So at some point, but this is dictated by random chance, all of the clusters will cross over to the intervention. And by the way, it can be one cluster crossing over in every step, or it could be multiple clusters. And in fact, the methodology is still developing, but there are some recommendations and some results coming out that suggest randomizing only one cluster to cross per step may not be the best idea. And we probably ideally want to have at least 2 clusters in each of the steps. So, but we see lots of examples with only one cluster crossing over per step. It also has implications for your power, how many clusters cross over per steps. The more clusters, if you have a design with only one cluster crossing over per step, you obviously end up with more periods and more data. So that does tend to increase your power. But there is a little bit of a statistical trade-off in that our analytical models don't seem to work as well when there's only one cluster per step. So we have to figure out how to balance these concerns, the power consideration and the kind of the ability to fit the statistical models that we need to fit. Anyway, so deviating from what I wanted to say. So this was still just explaining the characteristics of the stepped wedge. So these clusters cross over gradually. And then the third key feature of a stepped wedge is that it is a longitudinal design in that we are actually repeatedly taking outcome measurements from each of these clusters over time. So in each of these kind of cluster period cell, we take measurements. So it's longitudinal, and the intervals have to be long enough, of course, to allow you to actually measure outcomes. So a stepped wedge is not going to work well if you have a very rare kind of disease outcome, or you have a design, or you have a scenario where there's very few eligible patients for your trial, because then each of these intervals is going to have to be exceedingly very, very long to allow you to recruit or include enough patients to have data in each of these cells, right? So we don't want to have a design where there's lots of zeros here, because it's just not going to work that well. So the stepped wedge really works ideally when we have something that's fairly prevalent. We have access to routinely collected data so that it's not a lot of work to capture these repeated outcome measurements in each of the cells. And, it's not something like a very rare event. That's kind of the situation where a stepped wedge works well. Anyway, so these are the key features of a stepped wedge design. And then there are two main variations of the design: a cohort versus a cross-sectional stepped wedge. In a cohort design, this is more rare, where we have people present, prevalent patients in the clusters at the beginning of the trial. This might happen, for example, in nursing homes, where we have like a captive audience, and we have the patients that we can identify at the beginning of the trial. They start in the control condition, and then as the clusters start to cross over, the same patients are still present in those clusters, and we measure their outcomes repeatedly over time. So by the end of the trial, each patient will have contributed data in every single one of these cells. And of course, as a corollary, all of these patients will eventually receive the intervention. So in a cohort design, not only do all of the clusters switch over, but all of the patients also switch over from control to intervention. All right, so that's one variation. But by far the more common variation is a cross-sectional design. Some people also call this continuous recruitment short exposure. Here we have kind of a continuous flow of patients coming in and then going away, and coming in and then going away. So this might be in like a hospital setting or an emergency department, where we kind of initiate the trial. Patients come in, they get exposed to whatever condition the cluster is in at that point, then they go away. They have their outcomes measured and they go away. And then in the next period, there's more patients coming in and out. So this would obviously be completely different patients in each of these cells. So it's called cross-sectional because it's all different patients. But note that with this design, it's true that all of the clusters eventually get the treatment, but not all the patients. We're still going to have about half of the patients in the control and half of the patients in the intervention. So this resembles more kind of like a multi-center patient randomized trial, where we don't have this crossover at the patient level. All right, so those are the two main features. So here is I quickly tried to find an example in transfusion. I can't remember where this was published, but perhaps you know some of the investigators here. So the background here is that point of care tests can be used during cardiac surgery, I think, to reduce the risk of blood transfusions. And so they wanted to evaluate whether this point of care blood test within the context of this larger transfusion algorithm can reduce red blood cell transfusions. So this was kind of a complex algorithm that was implemented within these hospitals. And it made perfect sense that they had to use cluster randomization because it would really complicate things if you asked clinicians to follow this algorithm for only some of their patients and not for the control patients. That obviously would make no sense. So cluster randomization is clearly justified. They decided to do a step-wedge trial. They had 12 hospitals participating in this trial and over 7,000 surgeries. This was in Canada. Their primary outcome was a binary outcome, just the use of any red blood cell transfusion within 7 days. And there are actually very few trials, step-wedge trials with a statistically significant result. But here they did observe a significant reduction of relative risk of 9%. Relative reduction of 9%, and that was statistically significant. So very nice example. Here is the diagram of their design and notes. So here they had these 6 groups of hospitals. They call them groups. We call them sequences or rows of this diagram. In each of these rows, there were 2 hospitals crossing over at a time. So that's nice. Total of 12 hospitals there. And so they had monthly intervals. So this was, 6 rows and 7 columns, so 7-month trial. These numbers within each of these cells were the number of patients that underwent surgeries and were included in the trial. So quite a large number of patients in every cluster period. And these are all, of course, different patients. So they compared the rate of red blood cell transfusions within 7 days in all of the gray cells versus all of the blank cell, the white cells, and they observed this 9% relative reduction. Okay, so they could apparently turn on the intervention instantly. So often we see that this crossover from control to intervention isn't seamless. It might take a little bit of time to implement this new intervention. Sometimes it requires some educational strategies or some other implementation strategies that can't just be switched on instantly. And obviously sometimes you can't do all of that training or put those procedures in place at the beginning of the trial because that would lead to contamination, right? You want these control periods to be uncontaminated. So we do have sometimes what we call an implementation period or a transition period in between the crossover. And that transition period can be an entire step length. So you could just say, okay, that very first month after the crossover, I'm not going to collect any data because my intervention is not yet fully implemented. I'm only going to start in the next cell. So a variation of this design might be to just omit that very first month after the crossover and then start data collection again in the next month. But perhaps in this example, that wasn't necessary and they could just seamlessly cross over. So my discussion here today is just for the very basic design. There are also now fancier design that also omit some of the other periods. We call them kind of staircase designs, but I don't have time to get into that. And we also have batched variations of these designs. So the methodology is rapidly developing, but I'm just going to start with the simplest one for now, okay? And so in the next section, I just wanted to review some of the advantages and disadvantages. And I want to say again, I don't want to make you negative about these designs because if they work well and they have a good justification, I think they are, way better than the alternative, which would have just been an observational study. It would have just been implementing an intervention somewhere, maybe across all of the sites in your network, and then taking a measurement before and a measurement after. Well, we know that's the weakest possible study design. In a before and after design, the intervention effect is completely confounded with secular trend and just natural chance variation. It's just very, very poor design. So yes, the stepped wedge is certainly better than the alternatives. but it still has several disadvantages that we just have to be mindful of in order to do good, robust research. So some of the advantages, and I think there are really two key ones. We've done some systematic reviews about how people justify or explain why they chose a stepped wedge, and there's a lot of confusion about the strengths and weaknesses of these designs. I think there are really only two key ones. The first one I think is practical. Clinicians that I speak to and who really want to do this design tell me that, oh, it really helps recruit clusters for my trial if they know they are going to receive this new model of care, or they're going to get a chance to implement the intervention at some point during the trial, right? So that seems to be a really attractive thing. You don't have to tell them, oh, you have a 50-50 chance of getting the intervention, and maybe you're just going to be in the control arm, and all you have to do is collect data. You're not actually getting anything new or anything different. So that would be a criticism of a parallel arm design, right? Where half of the clusters are never going to get the intervention. Sometimes I try my luck and I say, okay, well, how about just offering the control sites the intervention at the end of the trial? But they don't like that. They want it to be part of the trial. But, there are examples of these types of designs where you finish the study, and then if you see the intervention is effective, you just offer it to the control arm at that point. Okay, so that's an alternative. But the second advantage, which is really difficult to argue against, is that the Step-Wedge can give you more power. So it is entirely possible that we do the sample size calculation for a parallel arm design, and number of sites are often very limited. We don't have a lot of sites. And with the available sites, a parallel arm just is never going to give you the desired power, but a stepped wedge does. So there are situations where it's the reverse, but for the most part, stepped wedge trials do give us more power. Okay. And I mean, the reason is kind of intuitive. Maybe you've thought about this already. It's because a stepped wedge has this nice feature that we use both between cluster comparisons, like in a parallel arm design, right? We compare between clusters. We compare the outcomes between the intervention and the control clusters, which is what we do in a stepped wedge partially. But we also have this within cluster comparisons. We have information about both the treatment and the control arm within the center. Remember, that's what I said earlier when I said we lose power by, in a parallel arm design, just adding more patients to the same cluster, to the same arm. We don't get that between between intervention versus control comparison. But a stepped wedge solves that issue partially, right? So in a stepped wedge, we've got information within each cluster as well that informs this treatment versus control contrast. So that's the strength. That's why our power goes up. But it's only partially because we also have the between cluster comparisons as well. So anyway, it's really difficult to argue against this. If my sample size calculation works out and I get more power with the stepped wedge, we often just don't have the budget or the resources to recruit many clusters into these trials. Okay, but there are some disadvantages that we just have to be mindful of. So there are some additional risks of bias. There are some additional statistical complexities, and there are also some logistical challenges. Often people do not appreciate the logistics of these types of trial designs. They can be really difficult to pull off. Let me just quickly review them one by one. So the first risk of bias is that we have a confounding by time. There's what we call a period effect. A period effect means that, well, outcomes often change naturally over time, even without intervention. So if I just observe outcomes over time, even not putting an intervention in place, we often see, oh, there's a natural improvement. Things just start to get better because people are aware that practices need to improve, and things start getting better because people, become aware of an issue. So in a stepped wedge, we do have these repeated measures over time, and it could be that some of that improvement is just, it would have happened anyway, even without the intervention. So we have to implement special statistical methods to account for these secular trends and to tease them apart from the intervention effect. So we have to rely on a statistical model that controls for the period effect. We cannot just do a chi-square test. We cannot just simply compare, like in the transfusion example, all of the gray cells to all of the white cells. We can't just statistically compare all of the intervention data versus the control data. It's not going to work. A chi-square test is going to give us a biased answer. Even a test adjusting for clustering is not going to give us the right answer because we have this problem of a period effect. And so we have to do a multivariable model that controls for the period effect in the analysis. And I often see that when you adjust for the period effect, your statistical significance goes away. So if you implement your model, even adjusting for clustering, but you don't adjust for the period effect, you get a statistically significant answer. But once you add that period effect into your multivariable model, the statistical significance goes away. And sometimes we have examples where it even inverts. So where you might have a beneficial effect without the period effect, it becomes harmful when you adjust for the period effect. So we see that some people say, oh, I didn't adjust for the period effect because it was not statistically significant. Well, that would be completely wrong. You can't make the argument for adjusting for the period effect based on statistical significance. It's an inherent feature of the design. We have to adjust for the period effect, otherwise we won't get the right answer. So it's very tempting at this stage to omit the period effect, but we know we cannot do that. There is this issue of time varying intervention effects, which we have to be very mindful of in a Step-Wedge trial. So it could be that my intervention effect changes over time, maybe because of a pandemic or something else happening in the health system. So if I compare between the clusters in these vertical periods, I may get a big effect in period 2, but no effect in period 3. That may just also be chance, of course, but we have to start thinking, well, is there something else happening in the health system or over time? Or maybe there's a seasonal effect that can kind of distort my intervention effect. So that refers to kind of a calendar time varying treatment effect. But there's another time varying treatment effect that we also have to be concerned about, and that has to do with the duration of exposure. So you can see from this diagram, some of the clusters get a lot of practice with the intervention, right? This first set of clusters gets 3 periods of exposure to the intervention. The final set of clusters just get 1 period of exposure to the intervention. So it could be that clinicians get better as they kind of do the treatment or the experimental intervention repeatedly over time. And so the intervention effect may not be stable over time. And we actually have statistical results that show if you ignore this issue, your time averaged treatment effect estimate could be completely wrong and could even be in the opposite direction. So by failing to account for this time varying treatment effect, your overall pooled estimate of what the intervention is doing goes in the wrong direction. Okay, so it's a big issue that we have to be mindful of. Perhaps I would almost be tempted to suggest that a Step-Wedge trial is not going to work well when your intervention works gradually. Step-Wedge is actually better for interventions that work immediately. Some other statistical complexities that arise have to do with this intracluster correlation coefficient. There are actually in a Step-Wedge design 2 types of correlation coefficients. There is the within period ICC. That refers to the correlation between patients included in the same period. But there's also what we call a between period ICC. And that refers to the correlation between patients who are in the same center, but they are recruited, say, many months apart. So somebody recruited in period 1 and the final period, their correlation may be weaker than the correlation between two people recruited in exactly the same period. So that complexity can also influence our p-values and give us wrong answers. So we have to include a more complex type of correlation structure in our hierarchical model. If we don't do that, again, our p-values might be too small. So that needs to be considered in both the sample size calculation and the analysis. And then some of the logistical challenges that can arise. Well, one issue that people perhaps don't appreciate is that all of the clusters have to be randomized at the same time. So it's not like a parallel arm design where sometimes people let clusters submit for ethics, get the approval, and then they can start. In a Step-Wedge, they can't start. They have to wait until everybody is ready. All of the ethics approvals are in place because we have to randomize the sites as to when they can start the trial. So, and also clusters have to adhere to the timing of the crossover, right? They can't just implement when they think they are ready. So in the transfusion example, we have these specific calendar times. This is when the design dictates they have to cross over, and this defines the intention to treat analysis, right? So clusters cross over when they are randomized to cross over, not when they feel ready. And we often actually even see sites be so eager to implement the intervention that they're not willing to wait, especially the ones that get randomized to go last. They just don't feel like waiting until the very end of the study. So they start doing things in some of these control periods to get ready. So the logistics, getting everything to be anchored in calendar time can be a huge problem. And then also, if we realize partway through the trial, oh, I actually want to, I might not have enough power. I have a suspicion that the recruitment of patients or the identification of patients hasn't been going that well. I want to add some additional clusters. Well, that's more difficult because any cluster you add now is not going to be randomized to the time of crossover. So it complicates things a little bit. So all of these complexities make me typically advise clinicians to consider a parallel arm design rather than a Step-Wedge if they can. But if that is not feasible, then I'm always happy to help with the design of a Step-Wedge trial. It's a really interesting trial. So just some of the key recommendations for a Step-Wedge: use it when you have a good enough reason. Make sure that you always account for the period effect in the design and the statistical analysis. Don't try to make an argument that I don't need to account for the period effect, because we know that treatment effect estimate would be biased. We have to account for this more complex correlation structure in our sample size calculation and analysis. And we have to be mindful of potential time varying treatment effects. So make sure that when you do implement this intervention, that you think about, okay, how is it going to work? Is it truly going to lead to like an instantaneous effect so that it makes sense to pool all of those intervention cells together and contrast them with the control cells, as opposed to something much more complex, which looks for different treatment effects in the different vertical periods. So that would just be a lot more complex. So I actually, I think I was asked to leave time for discussion. So I have more material, but I can pause at this point and we can discuss.
Well, I would, I think we've had some interesting counter positions put into the chat here. So I think it would be great if we could take some time to air those out.
Yeah,
So I'll
let's
call
see.
it Ryan, if you're still here, if you wanted to maybe summarize your position as you put into the chat about the role of these trials. Maybe Ryan is not at his desk right now. Well, I will. Maybe I could. Oh, there he is. Sorry, he's
Okay.
at a
Well,
coffee
I can.
shop. Okay, so you can
I
debate
can.
him without without his.
Yeah, I can just read the comments and address. So trial of last resort is underselling a bit. Yeah, I think I think I probably am perhaps taking the counter position deliberately, because I think promoting these trials as something desirable is just something that really worries me, because why wouldn't we just do all of our trials like that then? What's going to happen to patient randomized trials, which I just think are a higher level of evidence? And so I think we definitely just have to think carefully and perhaps work with a statistician who can implement some of the power calculations for you under alternative design. So don't commit to saying, okay, I want to do a step wedge or, one of these fancier designs off the bat. Perhaps just explore, well, maybe it is actually going to be cheaper to do a stepped wedge or a parallel arm design for that matter, because of my power assumptions. So
It's interesting. I was thinking as you were giving your presentation, that obviously this trial design involves, taking on a bit of additional statistical risk for the benefit of speed of enrollment and scaling up your trial quickly. And I was thinking, is this sort of like electronic cross match level of risk benefit, or is it like Bitcoin? And so I think you've spelled out kind of the tension between what the clinicians want to do and what the statisticians feel is best practice. Donnie, you got your hand up there. Do you have a question or comment?
Oh, hi. Hi, Monica. Thank you so
hi.
much. Really great to always hear you talk. I'm always enlightened. I wonder about so the value of randomization in an individual patient trial is obvious because you're going to allocate people to two different groups, and all the other factors that you're not thinking about would potentially be balanced or hopefully be balanced. But randomizing in a cluster step wedge trial seems a little arbitrary to me. It's just the timing when a certain cluster is getting randomized. Maybe you're early, maybe you're a little bit later, maybe you're later. What is the added value of randomization in that setting? Is it actually balancing anything, or it almost feels like lip service? Is it
Yeah.
not lip service?
No, no. We do need randomization. And that has to do with that idea of the secular trend. So when we do our statistical model, so our statistical model has like a term for period, right? So and then a term for intervention. That's a very simple statistical model. And the assumptions underlying that statistical model need randomization to become valid. The assumptions are all of these different rows have the same secular trend. That's the assumption, because you're not allowing each of the rows to have their own secular trend, like a different systematic variation in how they kind of like what's happening in the background. So the randomization guarantees that in theory, right? It says, okay, my 6 rows they're going to yield a common secular trend across all of these hospitals. And that's what the randomization does. So the baseline level and the baseline trend is equally distributed across the rows.
Okay,
And it
awesome.
also protects a little bit against kind of how how any kind of external shocks are going to influence the system. That hopefully that happens kind of in a balanced way across the rows.
Perfect. Thank you.
Okay.
Okay, not seeing anyone else with their hands up, I'll jump in with another question. I have to say, I feel like this is a presentation that rewards hearing it more than once because it is complex and there's a lot of nuance to this. I think one thing that I took away from what you said today was it's reasonable to take this kind of cluster approach when the difference between your two interventions is so large and complex that pivoting from one to the next is going to be difficult. So, like, the example of the transfusion algorithm that was the intervention for the trial that you were reviewing here. randomizing by patient, pivoting back and forth would be so challenging to do that it really would not work. But the other scenario that I've seen cluster randomization proposed for is when there really isn't actual clinical equipoise. You know, you have an entire hospital that just believes one thing, or like many clinicians are just, they are truly committed to a certain, intervention being better than the other and won't participate if it's a patient level randomization. They will only participate on a sort of a cluster-based approach. From your perspective, is that a legitimate reason to do a cluster-based trial design as opposed to a patient-level randomization when there's just not true individual equipoise at the clinician level?
I don't think so, unless I'm misunderstanding that argument. I mean, equipoise absolutely has to apply because you can get randomized to either the control arm or the intervention arm. So you cannot be absolutely committed to doing only one thing or the other, right? I think so. Even for a cluster crossover or cluster or Step-Wedge or whatever, you would still need to verify that the participating centers or the clinicians are in equipoise for participating. If they have a strong preference for one or the other, well, they can't really participate in this trial. So,
I
yeah.
think the appeal of the cluster approach is that if you're sort of taking like everyone's going to transition at some point from what they're currently doing to this shiny new thing,
Mm,
then you can sort of say, sure, I have equipoise enough to wait my turn, but
mhm.
you're eventually going to get that thing, which you
Yeah,
may or you then stick with afterwards. So I think that's sometimes is kind of
yeah.
the bauble of the cluster approach is that.
Yeah, but I prefer, and I understand that, but I prefer not to think about that as an ethical imperative. I don't think there is an ethical reason why, you have to do the Step-Wedge. And there are published papers that like fully tease apart all of the philosophy and the ethical arguments for that, because if there is an ethical imperative to give people something, to do something, you have to do it. You can't kind of delay giving it in some sites. Like that just means, well, there isn't an ethical imperative, because if there were an ethical imperative, you had to do it right away. You can't randomize. So I understand though, it's like an issue of, well, maybe you really feel you need to implement this, but you lack the resources to do it instantly.
Mhm.
And it's going to be rolled out anyway in a gradual fashion. So we might as well evaluate it now and use randomization for that purpose and just make it a much stronger design than a before and after.
Mhm.
So that I understand, but I don't think I want to say that it's got an ethical imperative.
Okay. There's another question from Ali Tabatabe in the comments. Let's read it out. I'm just pondering this, and I'm not sure if you mentioned this. For more chronic interventions, when a patient is assigned to an intervention, but then the cluster switches, does the patient switch too, or is their intervention determined only by the time of enrollment?
Yeah, so that depends on the specific trial scenario. So in some trials, if you have like a cohort design, like these types of trials might happen in nursing homes or schools or something like that, where they're kind of prevalent. They just remain, they keep coming back for treatment, then you may need to let the patient switch over to the new intervention. But the vast majority of trials are cross-sectional, whereby they get exposed to the intervention only for a short period of time, but then they kind of go away. And they might have a chronic condition, but they go away and they only followed under the original intervention that they were in when they got first exposed. So their outcome measurement then kind of is away from whatever happens in the hospital. The hospital might switch over in the meantime or something else, but the patient isn't affected by that. They just kind of get followed under the initial exposure. So
So
that would be, yeah,
whatever they were originally randomized to, they stay with.
yeah,
Okay.
exactly.
Okay. All right. I don't see any other questions or hands at the moment. Do say lots of thank yous in the comment section. I will join that as well. Great talk, so helpful. And I think it's really useful to kind of lay out the tension, between doing things perfectly and doing things quickly, which I think this is a good example of.
Yeah.
So thank you so much.
Thank you very much.
And with that, we will adjourn. And hoping everyone is able to join us next month, when we will be, what are we doing here? We are going to have Ryan speaking on adaptive trial design. So very much looking forward to that. Okay. Thanks, everyone, and
Great.
enjoy your holidays.
Thanks.
All right,
Happy
bye-bye.
holidays. Bye.